Hello, welcome back to our topic one. Okay, now we are going to talk about the speed flow density relationship and their interpretations. This one, Q equal to U time K, I do believe that you already learned during your secondary school. Okay, which is Q is the flow rate equal to speed, the U, okay, time with the density. Alright, so this speed, density, and flow rate have their own units, right? For example, the Q, whereas the flow rate is a vehicle per hour, which is how much the vehicle for that particular time. All right, that is a flow rate, or it makes you much easier to understand how much the car that passing through your car actually during a particular hour. That is what we call as flow rate. And then speed is in a kilometer per hour. How what is the distance during the time be given, and the K density will be the vehicle per kilometer. What how many cars on that particular distant road? Okay. We take a look for one example, a simple one. If a highway lane were observed to have a mean speed of 55 km per hour and a density of 25 vehicle per kilometer, the flow rate in the lane could be estimated as simple. Given to you the speed 55 km per hour and the density 25 vehicle per kilometer. So it's already been given to speed, given to density, they ask you to get the flow rate. So it's very simple. Q equal to U times K equal to 55 km per hour be given from the equation, time with 25 vehicle per kilometer be given from the equation, we get say 1375 vehicle per hour. Okay, so this is the flow rate. Okay, the next one is to show you how it looks like. Okay, for a graph. Okay, the relationship between one unit to another unit. For example, the first one we have about three: the speed versus density relationship, speed versus flow relationship, and also flow rate versus density relationship. Okay, so they have two. All right. So the next one will be the first one, which is the speed versus density relationship. Speed versus density relationship is whereas we are going to use this formula. Okay, U equal to UF minus UF over KJ times with K. Okay, if you take a look from here, okay, this is U. Okay, U is the speed versus with the density. We will find here we have UF. What is meant by UF? UF, the free flow speed, means that at zero here, the density at zero here, there's no car, so it's only you alone. So you can use what is the distance that you want to be is up to you. Okay, this is what is meant by here. All right, and then we have kj or the jam density, whereas the speed is zero because there's a too many cars already. The density is too packed here, so that's why the is considered as a jam density. All right, and then we have the speed at capacity, okay, or the density at the capacity, okay, uc or kc. Okay, so this one will be the maximum capacity here. Okay, the maximum capacity with the middle. Okay, the middle of U, which is UF over 2, okay, UF over 2, or the middle of KJ, whereas KJ over 2. Okay, so you will get the capacity, maximum capacity here. So you can see here, okay, you can see here, the condition at A will be the stable flow. Okay, might be during non-peak hour, and during the B is the unstable flow. Okay, it's a logically okay. Supposed to be the data for this one we consider as uniformly distributed, means that it's a linear. If you get the data correctly, for sure they got a sagging here, something like that, have something like this. All right, but for the study purpose, we assume that it's going to be straight. Okay, so says that you are driving a car in the weekend, a public holiday, no, cannot public holiday, we can say weekend, maybe some of the village area, and then you start drive. Okay, the traffic is zero, and then suddenly from time to time there's more car, and then your speed will going to reduce, more car, and then you're still okay until you reach here, okay, the maximum capacity, and then you found out that it started to jam already until you cannot move. So this is how the speed versus density relationship can be happen. All right, you take a look for this one. Okay, okay, stable flow. I think everyone's have and are very happy if you go for a very stable flow condition when you drive a car. You can drive very fast, but when you come to the unstable flow, then you're going to see that there's more car, and then once there's a car in front you stop, then you slightly going to reduce the speed slowly until you okay collect lah. All right, the next one will be UQ relationship. Okay, UQ relationship, which is the speed versus uh, the flow rate. Okay, so if you take a look on the formula, it's going to be Q equal to U time Kj equal minus with Kj over UF time with U square. You can see this U square here automatically, you know, is actually a parabolic graph. All right, it have the same condition, which is with the previous one, the speed density relationship. Where we have the free flow speed. Okay, we have the maximum capacity. Okay, and then we have the speed at the capacity. All right, and then we have what else? Okay, we have this is just another data, and then we have QC here. Okay, at the capacity. Okay, so it's going to be the same. Okay, now it's between the speed versus with the flow rate. So it's going to say like this. Okay, when you drive a car, and then suddenly it's okay, you just follow, it's still stable, and then suddenly the flow rate, I mean the car that passing your car more decreasing. At the first place, quite a lot of car can pass by you. Okay, at the first place, okay, until one level, because there's too many cars, there's less car that can pass by you because there's no more spaces. Then the speed also will be decrease. All right. So that is mean by that. Okay, so until here. All right. The next one will be okay. We take a look for this one, the speed flow relationship. If you can see that when during the stable flow is very fast, and then during the unstable flow, you found that the car increasing. So the car that want to passing by one checkpoint or is passing by your car decreasing on the speed itself, okay, because there are too many cars in front, then there's no space for you to there's no space for the other car to pass by your car. Okay, and the last relationship will be the density flow rate versus density relationship. All right, the formula will be Q equal to K times UF minus with UF over KJ times with K square. All right. So it's going to be the same. You're going to have the maximum, okay, maximum capacity here. Okay, then you can get the kg. All right, the kg. This is the kg is half. Sorry, kc. You can get the kc. Whether the kc is half from the kg. All right, and then qc also can get from here. Okay, so if we take a look for these conditions is whereas for example the flow rate versus the city, okay, you can see that the flow rate condition, I mean the flow rate and also the when there's an increasing of the density, flow rate will be okay up, go up to one level, that when there's too much then it's going to be reducing. Okay, All right. So this is based on the condition of I mean the numbers of vehicle from both sides. Okay. So if you take a look, if you understand properly, you can see that actually all of it is actually connecting between each other. Whereas we can say that it's like a technical drawing. Okay. Okay, technical drawing. You can see from here KJ, from here to KJ, from here you will see that you can get the capacity condition. Okay. Okay, this is just want to show you how it looks like. Okay, the same one when it comes to too many cars, they're going to reflect on the condition of the traffic itself. Okay, slowly when there's too much car, slowly decreasing and decreasing. Okay, all right. Okay, this is just want the same thing. Okay, you can see here. This is one example. Okay, that in China, when there's a dam density, I do believe is already like at the zero, at the kg one, kg condition. Okay, the car cannot move, and this is what happened in China. Okay, it's congestion up to 90 kilometer, and I do believe this one during their festival Chinese New Year. I do believe that way. Okay. Let's take a look for one example. Traffic volume during a stable free-flowing condition is 600 vehicle per hour with an average speed of 75. Okay, so they got the free flow, okay, of 60 vehicle per hour with an average speed of 75 kilometer. Okay, the speed. Okay, and also the queue, right? Estimate the average of traffic under congested situation for the same volume traffic speed and density are linearly related. Okay, linearly related. The maximum free flow speed for the road section is 90. Okay, 90. So now it's going to you have Q and U. So we can go for um, QU relationship. Okay, Q relationship. So first you sketch the probability curve for the Q relationship. You know, right? Okay, this is simple. I think if you try to draw first, then you can understand more. Okay, so it mentions that QU relationship, you already know. Okay, and then he mentions that Q2, okay, Q1, sorry, Q1 is 600. Okay, Q1 is 600, and then UF, Q1 is 600, stable flow. Okay, and UF is 90 kilometer here, the maximum 90 kilometer. Okay, average mentioned here is 75, 75, right? 75. Okay, I'm using my mouse, so I don't have a pen. All right, so this one 90, this one 75, correct? So they ask you Uh, uh, as average speed of traffic under congested situation. So you know already this one is stable. This one is congested. So the question asks you, what is the average speed? Okay, so this is will be the average speed. U2. Okay, average speed. This is the average condition lah. A and B. Alright, so you know already 90, 75. 0, what will be the value here? Actually, you can know that this one is what we call that is linear. Means that whatever value here, the dot here will be the same here. For example, here, how to say? Here, I change the other color. What the difference between here is going to be 15, right? 90 minus 75. So for sure here also will be, the distance will be 15. So the question asks you, what is the average speed? at the congested area here, average speed U2, so we can get 50 kilometer per hour. So it's much easier for you to calculate when you understand how to use this graph. Okay, so you can, if not, then you can go for the calculation part. Okay, but this is the best way for you to show lah. Alright, for you to show. Okay, the same thing actually. So you can get here the free flow is the average speed during the traffic under congested here is 15 kilometer per hour. Alright. Okay, the next example will be the vehicle in traffic stream move at an average headway of 2.2 seconds. The average speed is 80 kilometer per hour. Estimate the flow rate. Let me check. Flow rate is Q and the density is K. So what will be the solution? The solution will be that we are using the formula of Q equal to what UK or Q equal to 1 over H. Just remember headway, right? Headway equal to 1 over Q. Okay, so sama lah. It's going to be the same. Alright, so we're going to use this one. Okay, so use Q equal to 1 over H. Okay, just put 1 over 2.2 second, you time with 3600 to change it to the hour, then you will get 1636. Okay, and then by using the formula of Q over U times K, you will get the K. Okay, so the K equal to Q over U. You already got the Q. Okay, you already get the speed here, 80 kilometer per hour. Then you will get the answer. Okay, Q here. Okay, beware that once you check wrong here, calculate here, then you're going to wrong calculate here. Okay,